Hello, my name is Giovani Guizzo. I'm a research fellow at University College London, and today I'm going to present to you the paper Enhancing Genetic Improvement of Software with Regression Test Selection. This is a paper I wrote with Dr. Justyna Petke, Professor Federica Sarro, and Professor Mark Harman from our group, Solar. For those of you who don't know, I'll briefly introduce the concept of genetic improvement, or GI for short. GI aims at getting an existing software and automatically modifying it to improve a given software property. This property can be functional or non-functional. For example, in automated software repair, a type of functional improvement, we get a failing software and try to generate bug-fixing patches. In non-functional improvement, on the other hand, we aim at improving properties such as runtime, memory consumption, and energy consumption. For that, we represent the software into a genetic representation and apply modifications to this representation. For instance, we can represent it as a tree or a list of statements or line. Then we can delete statements, swap lines, copy blocks of codes, and so on. GI works over many iterations, generating one software variant at a time. The idea is that the variants will maintain the desired behavior of the software while improving the target property. To check whether it occurs, we use the test suite as an oracle. Hence, each generated variant is tested against the test suite. However, as one can imagine, running each software variant against potentially thousands of test cases incurs a great computational cost. One way of solving this problem is to select only relevant test cases, as opposed to using the full test suite. This can be done with the usage of Regression Test Selection, or RTS for short. Usually, RTS techniques search for the test cases that cover the changed piece of code, be it with dynamic or static analysis. The idea behind RTS is that by using fewer test cases, the testing phase will execute faster, thus reducing the need of computational resources. We hypothesize that RTS techniques can and should be used as a core component of GI in order to reduce its cost. Prior work has showed the benefits of RTS in many contexts, but never for non-functional property improvement. In this context, different and unseen challenges arise. For instance, by speeding up the process of runtime improvement, the search itself is impacted because the runtime is precisely what guides the search. So, the main objective of this work is to investigate the impact of RTS on the effectiveness of GI for non-functional improvement, the magnitude of the efficiency gain when RTS is active, and the trade-off between effectiveness and efficiency in various application scenarios. We designed 3 research questions to evaluate our hypothesis. Research question number 1 focuses on analyzing whether RTS techniques are safe and whether they impact the final results of GI. RQ2 focuses on unveiling the efficiency gains obtained by using RTS with GI. And finally, RQ3 concerns whether different RTS techniques offer different trade-offs between efficiency and effectiveness in different GI application scenarios. For our experiments, we used Gene, an open-source GI tool for Java programs. It offers both functional and non-functional optimization algorithms. We also used 7 real-world software from the Apache Common Suite, and we compared the results with the usage of 4 different techniques: GI with no RTS, GI with a random RTS just for sanity check, GI with ecstasy. Ecstasy is a dynamic analysis RTS technique, and GI with starts. Starts is a static analysis RTS technique. Well, in our experimental procedure, the first step is to run the profiling procedure of each strategy. In the profiling phase, Gene gathers hotspots in the code so that it can focus the optimization of specific hot methods. This is where the selection is done. Without RTS, Gene will simply assign all test cases to all profiled methods. On the other hand, when using an RTS technique, the respective RTS technique will decide which test cases should be executed to test each profiled method. This information is stored and only a subset of test cases is executed in the set phase, which consists of the actual execution of the GI optimization process. We start execution time for both profiling and execution phases. The results of the GI execution is a set of optimized software variants. However, these variants are only tested against a subset of test cases, meaning that the RTS technique might have missed some important test cases that could reveal a bug. Hence, in the third phase, we execute the whole test suite against the software variants to determine whether this actually occurs. In other words, we want to know whether the software variants would fail if the whole test suite is used and no RTS was used. In the end, we compute the results in matters of effectiveness and efficiency gains. Okay, so answering research question number 1 about safety, we found out that it is almost 100% safe to use RTS techniques with GI. Out of 280 patches generated with the two state-of-the-art techniques, only one patch failed the full test suite. Moreover, we also found out that the relative change in improvement, in other words, the quality of the solutions, improved with RTS by up to 5.81 times. On average, GI with RTS provided from 2.2 to 2.5 times better improvement with large effect sizes in 86% of the cases. Now, for the efficiency gain, we found out that RTS was able to reduce the cost of GI up to 68%. What you're seeing here is the relative cost of the GI process. For 86% of the programs using either ICSE or STARTS, we can obtain statistically significant savings with large effect sizes. This box plot shows the cost of each strategy over 20 runs. The red line represents the original cost. Any value above this line means that the cost of this strategy is higher than using no strategy at all, whereas values under this line represent cost savings. In summary, GI with ecstasy costs on average only 79% of the original cost, a reduction in 21% in running time, whereas STARTS was able to reduce it by 22%. This figure shows the cumulative cost of our experiments in hours of running time. In our specific case, GI without RTS used over 180 CPO hours to complete the experiment. For the same experiments, this time was reduced to 114 and 118 when using ecstasy or STARTS respectively. This is an average reduction of 64 hours of computational time, 2 days and a half. This is more than a third of savings when compared to the total cost of GI without RTS. To answer RQ3, we evaluated 3 GI application scenarios. In the first scenario, the engineer is concerned in finding the perfect improvement. In other words, the best improvement possible in seconds. In this case, using ecstasy provides the greatest runtime improvement for 4 out of 7 programs, whereas STARTS yields the best results for 3 out of 5. The second scenario is when the engineer wants to find a valid patch with a positive improvement as fast as possible. What you're seeing here is the median execution time in seconds before the GI process can find an improving invalid patch. In this scenario, STARTS and ecstasy showed similar results, but STARTS was a bit faster. The last scenario concerns diversity of patches. We want to know which strategy provides more valid improving patches. In this case, ecstasy showed the best results for 5 out of 7 programs. All in all, in most of the cases considered, 19 out of 21 comparisons, using GI with RTS provides better results than traditional GI without RTS. You can find more and better patches and considerably quicker than GI without RTS. So, the takeaway message here is, use RTS techniques in test-based automated improvement of software for significant efficiency gain with no negative impact on the results. This concludes my talk. Thanks for watching, and if you have any question, please do not hesitate in contacting me. Cheers!